over naming cycloalkenes in this video and going over dienes, thiones, and polyenes. So for naming cycloalkenes, for the carbon double bond in the ring, they're going to be, they're going to be on carbons number 1 and carbon number 2 is equal to the CC double bond in ring, and then you'll number the rest around the ring. If there's more than one bond or a double bond in there, then you start to go off of substituents as well. So if we do an example, to have a cyclohexene. So we have carbon 1 and carbon 2. Our carbon-carbon double bond is on carbon 1 and 2. And then we can number 3, 4, 5, 6. I could have done it the other way too. I could have started 1 down here, then 2 go up, and then go around. It's up to you. It doesn't really matter. It's just, I tend to go the other way. But whatever works best for you. Okay, so now what we write is this is a 6-carbon ring, which means it's cyclohexene, because it has a double bond, and the double bond is on a 1. So it's going to be 1 cyclohexene. We do this molecule. We have a double bond over here and a methyl group and another methyl group and another methyl group. Okay, so we want our carbon-carbon bond to be on 1 and 2. So let's do it the first way. We'll do 1 on the top, 2 on the bottom. I have 3, 4, 5, 6. This would give us methyls or substituents in general on 3, 4, and 6. If we went the other way, if we started 1 down at the bottom and then 2, 3, 4, 5, 6, we would have a methyl on 3, 5, and 6. So we always want the substituents on the lowest number possible. So the first numbering would be the correct one for this molecule. And because it is a 6-membered ring, it's going to be a cyclohexene again. The carbon double bond starts on a 1, or starts on carbon number 1, so it's 1 cyclohexane. And then it would be 3, 4, 6 trimethyl 1 cyclohexene, just like that. And that would be the full name of it. 1 cyclohexene is the name of this left one. So now we can do a molecule that looks like this. We have a 6-carbon ring with a group with 2 substituents on it and a double bond. So what we're going to do is we are going to first find the double bond, which is here, and we're going to make one side 1 and one side 2. We can make the first carbon at the top because it has a substituent on it. So that means that it is as close to the substituent as you get. So 1, and then the next one would be 2, 3, 4, 5, 6. If we went the other way, it'd be 1, 2, 3, 4, 5, 6. So the substituents would still be on 1 and 4 no matter how you name it, because they are directly opposite of each other, or how you number it. So it's up to you how you want to number it, or which direction you want to go. So this is a 6-carbon ring, and our carbon double bond starts on 1, so it's a 1 cyclohexene. We have a 1 methyl group from right there, and this is a 4 isopropyl group. I comes before M in the alphabet, so the name is 4 isopropyl 1 methyl 1 cyclohexene. So draw the formula. Let's draw the formula for 3-methyl cyclohexene. So first we're going to draw our 6-carbon ring. This doesn't have a 1 in front of it, so it's implied. It's implied that it's a 1 cyclohexene. So we'll do a carbon double bond, and we'll go 1, 2, 3, 4, 5, 6. It has a methyl group on 3, so our overall molecule would have carbon-carbon double bond on 1, 2, and a methyl on the 3. Okay, what's wrong with this name? 6,6-dimethyl cyclohexane. Well, first, this should be ene. It's the first issue. But we have cyclohexene, so we're going to draw our cyclohexene again. We're going to assume this is a 1 cyclohexene. So we have 1, 2, 3, 4, 5, 6. And we have 2 methyls on 6. So it's going to look like that. So this is what the molecule looks like, but the naming is wrong. So what we would need to do in order for our substituents to be as close to the double bond as you can, we're going to have to start at 1 at the bottom. So this one would be 1, 2, 3, 4, 5, 6. So the correct name would be 3, 3 dimethyl 1 cyclohexene. So they just numbered from the wrong direction. Cis-trans isomerism in cycloalkenes. Cycloalkenes, it's not possible to have trans configurations or isomers around the double bond. So the around the CC bond in rings less than 7 carbon atoms. They have seen one that is a cyclooctene, but a trans cyclooctene, but it's very, I don't think it occurs in nature. I think they made it. But so we have which cyclical molecules show cis and trans isomerism. So you can see here, this one is a no, because it has the substituents coming off of this double bond, and it's 1, 2, 3, 4, 5, 6. It's a 6-membered ring, so this can't have trans. This one, in order to have cis and trans, we need substituents on different carbons. These substituents are on the same carbon, so therefore it has no cis and trans. For B, you can have cis and trans. You would have, you could have this as a cis, or yeah, this would be a cis. Or you can have this as the trans, the wedged in the dashes. So this one is cis, this one is trans. And then for D, we can do the same thing. So this one has cis and trans as well. So if we do our wedges and make the cis version, this is cis, we can draw the molecule again with a CH3 going up and a CH3 going back, and that's trans. Again, it has an alkene, so this is a cycloalkene, and it has cis and trans, but the cis and trans are not off of this double bond. Because of this double bond, it makes it planar. So these two substituents can't rotate. They can't rotate around. So you can't have a cis and a trans on it because they're planar and stuck in that position. If you try to change it, you'll break the bonds. So dienes, trienes, and polyenes, this just means molecules with more than one carbon-carbon double bond. Di means 2, tri means 3, and poly means many. So that would be anything greater than 3. We can look at an example here. We have one double bond beginning and then one at the end. This is a 1, 2, 3, 4, 5 carbon chain. So it's going to be pentene because it has 5 carbons and double bonds. The double bonds start at carbon 1 and carbon 4. So this would be 1, 4, pentene, and since it pentene, we have carbon-carbon bonds on or at 1 and 4, which means it's a diene. So you would have a 1, 4 pentadiene would be the name. If we do another one, we can have this molecule. Again, we'll count the carbons. So 1, 2, 3, 4. This is a butene, 4 carbons. We have carbon-carbon bonds at 1 and 3. So there's 2, so that means it's a diene. And we have a methyl group on carbon 2. So this would end up being 2 methyl, 1, 3 butadiene. So that would be the name for this molecule. One more example is a cyclical ring. This is 5 carbons, so it'd be a cyclopentene. It has carbon-carbon double bonds. We do 1, 2, 3, 4, 5. Or we can do it the other way, where it'd be one, I'll put on the inside 1, 2, 3, 4, 5. Or you can have it as, so this is going the other direction, that's going counterclockwise. This is going clockwise, or we can start at this corner and go to the next bond. So only having one carbon in between there. And that numbering would be 1, 2, 2, 3. I'll erase the other ones so it's easier to see. Okay. So we could have 1, 2, 3, 4, 5. So now we have carbon-carbon double bonds on 1 and 3. So this one, which means it's a diene. So this molecule would be 1, 3, cyclopentadiene. Okay, cis-trans isomerism in dienes and trienes and polyenes. An alkane, or an alkene, sorry, with N, so some number of bonds, is going to have 2 to the N isomers, because you're going to have 2 per carbon-carbon bond. And these are cis-trans isomers. So for example, we have this molecule versus this one. Can number it. This is 1, 2, 3, 4, 5, 6, 7. This is a 7 carbon ring, so this is a heptene. Carbon bonds at 2 and 4, which make it a diene. And so it is trans to each other. So this first one is trans. You have H's on opposite sides. So this is the one on 2 is trans. The one on 4 has H's on opposite sides as well. So this is going to be trans. And you would write it as trans, trans, 2, 4, heptadiene. Now, if we go to this next one, we're going to number it 1, 2, 3, 4, 5, 6, 7. Again, it's a heptene, 7 carbon chain. It has carbon-carbon double bonds at 2 and 4, which makes it a diene. The carbon at 2 has an H down and an H up, so it's trans. 4, it has an H at the bottom and an H at the bottom. They're on the same side, so it's cis. Now the name is trans cis 2, 4 heptadiene. It's easier for me to look at the hydrogens to put them in and see if the hydrogens are on the same side or not, if there's substituents on all the other sides. But you can also look to say, oh, there's a branch off of the top on this side and the top on the other side of the carbon, and then those are cis to each other. Whereas this other molecule, you have one going up, one going down for the branches, and that's trans. Whichever way works for you, if you want to look right in the hydrogens and look at the hydrogens, or just look at the carbon chain itself, either of them work. It's just one way that I prefer. Okay, this one's a little tricky. We want to name the following molecule, specify E or Z. Remember, we went over E and Z in a previous video. So we are going to number them 1, 2, 3, 4, 5, 6, 7, 8, 9. We did that way because we have this double bond at the beginning of it. We can have that as a 1 and 2, and it has 2 substituents off of it. So that is going to give us our lowest number. So this is a nonene. We have carbon-carbon double bonds at 1, 4, and 6, which means it's a triene. We have 2 methyl groups. So we have a 4,6 dimethyl group. We have chlorines at 1, 2 on 1, and then 1 on 7 trichloro. So we got our chlorines, our methyls, we have our double bonds. Now we need E and Z. Remember, E and Z are high and low priorities. Priority groups. So we're going to look at each bond. So for this one, we have a Cl, Cl, H, and then the carbon chain. This one cannot have EZ because it has 2 of the same molecules on the carbon-carbon double bond. So we can't do a EZ on 1. So EZ at 1, 4, and 6 equals not possible. So now we look at 4 and 5. We have a hydrogen coming off that side. 1, 2, no, we don't. We have a CH3 coming off that side. So this depends on how you like to do it. The way I like to do it is a little different. I like to look at each bond. So this one has a CH3 coming off and the rest of the chain as one of them. This one has the rest of the chain coming off of it and a hydrogen. So if we look at the priorities, we have carbon is bonded to this carbon. This is the first atom you look at is carbon, and then this one is a CH2. So your first carbons bonded are all carbons. They're both carbons. So then you have to look at the next one. So this is now a CH. So this is CH, CH2 versus CH3. So this is going to be higher priority because it has carbon-carbon. Over here you have a hydrogen and the rest of the chain, which would be a carbon, starting with a carbon. So this one would be higher priority on this side because the hydrogen is always the lower priority. So 4 would be E because E is opposite. 6, if we look at it, we have again the methyl and then the rest of the chain. And then a chloro group and the rest of the chain, which is a CH2, CH3. If we look, we have a CH3 versus CH2. Okay, both carbons are the same. Then we go to the next one, which is a CHC or CH3 or CCH2, however you want to do it. But that has another carbon off of it. Well, this is just one carbon. So the higher priority is going to be going down. And then on the other side, the chlorine is going to be higher priority than a carbon because this one is carbon. And so the higher priority is going to be on the bottom as well. So this one is Z. So your name would be, I'll have to start over here, 4E, 6Z, 117 trichloro, because C comes before M, 4,6 dimethyl. Started over there and I still ran out of space. 1, 4, 6 non-triene. So there, the way I'll show you the way I like to do it, that sometimes lets me see it a little more, especially if it's a complex molecule. So if I look at the carbon-carbon double bond at 4 and 5, so you have carbon, carbon, this is carbon 4, this is carbon 5. We have a CH group bonded to the top, and then this one is a CH2, CH, C, Cl2. So that's the rest of the chain. Carbon 5 has a C, CH3, CH2, Cl, CH2, CH3. So that's the rest of the chain, and then a hydrogen. So you can see how this is higher priority than this whole chain. So this would be the E. For the carbon-carbon double bond at 6 and 7, if we do that, carbon 7 has chlorine coming off the bottom, and then a CH2, CH3 are the rest of the chain. On carbon 6, you have a methyl group on top, and then the rest of the chain on the bottom, which is the CH, C, CH3, CH2, oops, H2, CH. You wouldn't have to write all of this out if you didn't want to. Yeah, I think you would get the gist of it after a couple, but this I'm just showing you how I do it. You can see the chlorine is definitely higher priority, and so is the branch, the longer molecule. So this was, what was this? Yeah, so this was Z, because they're both at the bottom. It doesn't really look like the bottom, but if you have your plane, you have the chlorine on the bottom and the rest of the chain on the bottom. Whoa. On the bottom.